Right. Well, welcome everybody. Shall we get started? I'm sure a couple more people might still sign in, but that's fine. Thank you so much, everybody, for joining our Durham Energy Institute seminar today. Professor John Gluyas is going to be talking about exploring for hydrogen, helium, and lithium. Is it as easy as 1, 2, 3? We are recording this seminar. Just if anyone has any problem with that, just feel free to just mute yourself and turn your camera off. And actually, we'll ask everybody to mute themselves and turn their camera off during the talking as well, and we can turn them back on again once we get to a question and answer session at the end. So John's going to talk for about 40 minutes or so. John, is that right?
Yes, I think so.
40 minutes. And then we'll have some time for questions and answers at the end. If you have any questions and you want to pop them in the chat as you go, we can get to those when we get to the end. So John is a professor of earth sciences and the Ørsted Ikon Chair of Geoenergy, Carbon Capture and Storage at Durham. He joined us in 2009, before which he spent many years working in the energy industry. He's also recently been elected as the president of the Geological Society, so that's very exciting. And he's going to talk to us today about hydrogen, helium, and lithium. So thank you, John. Is that right? You all right to just go for it from there?
I'm indeed. I jumped out of the display view. Then can you see the screen? Okay.
I'm struggling to see the screen. I don't know if anybody else can see the screen.
Oh right, maybe did I accidentally kill the sharing? I do apologise. And now I've lost it. Share screen. There we go. Let's try again. How's that?
It's trying to start, I think. I've just got a blank screen at the moment. Oh, yeah, that's working now, John. Thank you.
Right, thank you. Sorry about that. Our bandwidth is not great here. So, I've given this talk a couple of times. It continues to evolve, and I've not actually looked at the slides in a little while. I did add one or two new ones in, but I'm desperately trying to write the paper that goes with this. I humbly thank my co-authors, Madeline, Rita, Barbara, and Chris. So, is exploring for helium, lithium, and indeed hydrogen as easy as 1, 2, 3? I always like to take the long view, and this is possibly too long a view. But if you think the development of and tools, and if you like, we've gone through a number of processes of the Stone Age, the Bronze Age, the Iron Age. It would not be unreasonable to think of the period of time which was the early part of the Industrial Revolution, the Coal Age, and now possibly for the past 100 years or so the Petroleum Age, although information is giving it a hard run for its money, as it were. But nonetheless, what will we be doing tomorrow? What will provide the tools and mechanisms to support the further development of humankind? A lot has been written about the next century being the century of metals, so return to not the Iron Age, but to a whole host of metals which will be critical for particularly low carbon technologies and so on. But it's not just the metals, not just the transition group metals of chromium, cobalt, nickel, copper, and so on, but a couple of lighter elements. And there are many tables like this you can pick up on different sites, whether it's the Royal Society of Chemistry, the US Department of the Interior, and so on. And nearly all of those will list hydrogen, lithium, and indeed helium as critical to that process. And here we see, I think this is from one of the societies, showing which are elements under threat or difficult to deliver, or were on the list last year or on next year. And both the EU and the US publish an annual update of what's required. So what I've been thinking about is how we can perhaps bring all these together. At the moment, lithium is hot to trot in terms of its utilization, principally in batteries, but also in ceramics. And the growth of that industry has been truly enormous. You look at just the share of vehicles and battery developments and so on. And each of these new technologies has a massive requirement. At the moment, we extract lithium mostly by evaporating what are already highly concentrated brines, mostly in what's called the lithium triangle. Why are we so fond of triangles? Which is principally in Chile, but also touches into Argentina and Bolivia, ABC as it's known. Some lithium is extracted from igneous rocks, pegmatites and so on, much of that coming from Australia. But the predominance is from the Atacama Desert, with massive environmental impact. For helium, this is a curious one. Helium is critical for the energy transition in that we build things like chips as in computer chips rather than potato chips, in inert atmospheres, and for that helium is a must. But it has a whole host of other uses as well, whether it's used in blimps and balloons, leak detection, and increasingly in supercooling and cryogenics. If any of you have had an MRI scan, then those big magnets, the big donut-shaped magnet, is chilled by liquid helium. And it's produced these days from a very small portion which occurs in a number of natural gas, in other words, methane accumulations. Since I put this slide together, I've actually calculated the accidental carbon footprint of the global helium industry. It's around about 320 million tons of carbon dioxide equivalent per year, about the same as the UK, or bizarrely Vietnam if you prefer. I'm not sure what the Wales unit is for that, but here we go. And hydrogen, well, hydrogen's very abundant on Earth, of course. The oceans themselves are 2 atoms of hydrogen for every 1 of oxygen. And the same would be true, of course, for fresh water and water which is buried within the crust itself. But it comes as a compound. And so to produce hydrogen, which again is seen as a critical component for the energy transition, because when you combust hydrogen, all you get is water vapor, we have to make it. And currently there's a large hydrogen industry around the world, but that industry makes hydrogen mostly from methane, sometimes from coal, and in what's known as the water-gas shift reaction. And one of the products of that water-gas shift reaction is CO2. And CO2 routinely, for 99% of the current hydrogen industry, is vented to the atmosphere. And so, although it's fairly cheap to make, as you can see on the graph on the right, there's a massive carbon footprint associated with the hydrogen industry, actually worse than if you burnt methane itself. Now, there are proposals, and we've begun very slowly to mop up that CO2, to collect it and bury it in CCS, carbon capture and storage programs, and the HyNet one from Liverpool will do just that. It's not a fantastic way of taking CO2 out of the system, and depending on how you do it, it's in some instances overlaps, not just in cost terms, but overlaps with the CO2 emitted from the grey hydrogen. Most people are now thinking they want green hydrogen, which is delivered by electrolyzing fresh water. But to do that, you need clean, green electricity. And the cost of that is high. Now, the cost will come down. But since you're going to manufacture this hydrogen, it's always going to cost more than the feedstock from which you produce it. So can we do better than that? So, I think I've already jumped ahead a little bit. My apologies. Just a whole host of figures. But in terms of hydrogen, if we're thinking about green hydrogen, you need some 50 megawatt hours to produce 1 ton of green hydrogen of electricity. I've already mentioned the figures for helium. In fact, the most 40% of all helium today comes from the giant North Dome gas field in Qatar. And the helium is present only as 0.04%, meaning that 99.96% is methane, or a tiny fraction of nitrogen. And you can see some of the figures for lithium as well. So whilst these materials are very desirous for the energy transition, they come with a penalty. Can we do better? So there's no shortage of hydrogen, but we need to deliver whatever we do at a cost comparable to natural gas. We clearly need to find more helium, and we need to find it without all those greenhouse gases. And we need to find a way of meeting lithium demand without the massive environmental impact of all these salt pans drying in the Atacama. So let's take a look at some of where geology can deliver on this. We know, for example, that hydrogen is produced, and I'll demonstrate some of the processes in a minute, but hydrogen is produced by the ancient granitic crust, the cores of each of our continents. We also know that the water rock reaction on the margins of those continents, and sometimes in the middle of them, produces hydrogen as a byproduct of this process called serpentinization. Helium, like the granitic crust that delivers hydrogen, comes from the same place. And we're finding increasingly that lithium is present in extractable quantities, particularly with some new technology from things like geothermal systems and even oil field brines, which are just not being used. I love this diagram because it was put together by a really good guy, Paul Nadeau, at what used to be called Statoil, Equinor, and it's a great piece of work, but it's put on, if you like, this golden zone between the green dotted line just beneath the surface there and the red dotted line. That's where you get your petroleum, and he called this the golden zone. But it, if you like, in ancient terms, what was beneath it might be seen on an old map as here be dragons, but it is the realm of helium, hydrogen and lithium. Maybe not all the way down to the moho, but certainly a big portion of that, which is shown in grey, is the material which will deliver these three elements into usage for the energy transition. So, having come from a background in the petroleum industry, my thinking is very much along the lines of, can we put together an exploration strategy for these three elements, which looks at the source, how that source is matured, how the product, whether it's hydrogen, helium, or even lithium, gets out of that source rock and migrates, where it accumulates, how it's entrapped, and really the final part of the story, how long it stays trapped. You know, helium, even in a steel container, stainless steel container on the Earth's surface, helium will migrate, will diffuse through the stainless steel and disappear off, beating Earth's gravitational pull. So hard to get hold of. Right, let me tell you a little bit about some of the work we did on helium, because it led, well, I'll show you where it leads in a minute. What we're concerned with was trying to understand how the helium is sourced, how it migrates, how it accumulates. And I had a student, Davina Danabalan, start in 2012, funded by Statoil at that time, on trying to understand these processes. And we, after many trials and tribulations trying to get hold of gases which contained helium, Di did field work in the Midwest of the USA, a known helium province. And you can see where she sampled. We took gases out of those. We looked at the isotopic composition. We looked, therefore, about how we might be able to understand the source of those. And then we got a lucky break, because a piece of this work was published in the conference, and we got a call from a couple of guys, friends, who was working on gold prospecting in Tanzania, and the other visiting him was a petroleum explorer from Australia. And they mused as they were in Tanzania and found an old book which had reported cold helium seeps in some of the ephemeral lakes a little bit further south from this volcano in the Rukwa region in the southern end of Tanzania. And that put in place a piece of field work. And you can see one of the postdocs we had working with us, Pete Barry, sampling some of the gas bubbles which come up from these rather short-lived lakes during the rainy season. Of course, the seeps are still there during the dry season, but you don't tend to see them. And when those material was taken home, I'll come back to what we did this in a minute. So we already had a big bunch of background, particularly from the Texas Panhandle area, which is historically the main production area for helium. It occurs at only 0.3% in the gas, but lots of work has been done to try and understand how helium is sourced from the basement, from the decay of uranium and thorium, and it becomes associated with nitrogen in a process we don't yet fully understand, and nitrogen acts as the carrier gas. So we've been working on that basis that we need to understand the nitrogen as well as the helium. But this opportunity to go to Tanzania was quite a breakthrough, because instead of finding helium present at 0.3% or even worse, like the Qatar gas field at 0.4%, we found helium present up to 10% in these seeps. World record concentrations. Importantly too, the rest of the gas, almost entirely, was nitrogen. So these were nitrogen helium seepages. Now, what we think is happening with the nitrogen, which is far more abundant than the helium, is that it reaches critical saturation in either through advection or bulk fluid movement or possibly uplift, and rather like the deep sea diver coming from beneath the sea and moving up too quickly, nitrogen bubbles form, and the helium, which really does not like to be in solution at all, partitions completely into the nitrogen phase, and that gives you this ratio of about 10:1. So these were helium seeps, and they're all over the place. Further work very recently in 2003 on helium was led by one of our postdocs in, actually a postgraduate at this time, in Oxford University, and published in Nature. And what she did was formalize that, I should say, Annie Chang, formalize that process in terms of doing basin modeling and looking at when you could form a free gas phase. And basically what we found was sort of two end members in the helium spectrum. This work was done principally on the Williston Basin, which goes from North Dakota into Canada. And helium here was being generated since at least the Jurassic, produced much earlier than that, exolved from at least the Jurassic, so 170 million years or so, and accumulating in reservoirs beneath some very good, tight, low permeability aqueludes. In Tanzania, we seem to have got there just in time. The system is actively generating helium at very high rate, but with a system which has some very poor seal rocks. So if you like, we've just got lucky. And there's a comparison here to be made with some of the petroleum systems. For example, in the Gulf of Mexico today, the source rocks are actively generating oil, and as much is coming to the surface naturally as spilled from the Macondo disaster of 2010. The shales which occur in the Gulf of Mexico are not very good, but they're holding up that oil just long enough for humans to be around to exploit it. Whereas if you go to North Africa, and in particular to Libya, there are oil fields there, notably Elephant, which has been in place for 500 million years. So we have whereby helium is simply a product of the decay of uranium. They produce mop-up helium nuclei, helium nuclei, and they mop up electrons. we need a system which liberates those helium atoms from the crystal lattice, and that's heating, which is why Tanzania, when we were suggesting we might look at it, was so good. It's got ancient Archean basement. In other words, any uranium and thorium there will have had time to decay to lead, or partially decay to lead, and produce more helium than a young system. And we've had a recent geological heating event which will knock the temperature above the closure temperature and allow helium escape from the crystal lattice into interstitial fluids and fluid inclusions and so on. Other than that, and we need some better entrapment process in terms of seal quality. Other than that, the systems are indeed rather similar. Once you get out of solution with the helium and nitrogen, it's driven by buoyancy and will follow a path not dissimilar to that which will be followed by petroleum fluids. And really, this is breaking news, because this is a number of wells have now been drilled in Tanzania. Helium One is the company that used our information and for which we provided analytical services and isotopes and so on. The new management of Helium One we're not associated with, more's the pity, but they've just drilled and flowed a well in the Rukwa area with 4.7% helium. And as it happens, hydrogen, but I'll come back to that in a minute. I don't know the full compositional data. This is the headline, which came out about 10 days ago. Right, let's move on. So we'll store that for a minute, and we'll spend a little less time on hydrogen and lithium. Lithium is a story which is still very much emerging, and active research from Madeline and PhD student Ella in Earth Sciences. This is the situation for hydrogen at the moment. Almost all hydrogen today is what you might call grey hydrogen, in that it's produced from fossil fuels and the CO2 is released. We can capture that CO2 and you can get to call it blue. Maybe we can get green hydrogen, but of course that requires fresh water, and that in itself is a problem. You know, the hydrogen industry at the moment is minuscule, and these droplets are supposed to illustrate that. The 2020 tiny blue droplet is the relative size of the hydrogen industry in energy terms compared with the oil industry, the black bubble. And what we need to get to by 2050, using the International Energy Association, is bubbles looking something like the bigger blue one. So enormous, lots of investment. This is the pattern I showed before, the hydrogen trajectory, if you will, with the aspiration, and the KPMG don't say how you get to this cheap green hydrogen by 2050. But nature produces hydrogen. Many of you will have heard of Chimera in Turkey, a natural seep, which is not methane. Many people think it is. It's near pure hydrogen. But probably the most exciting thing to have happened in 40 years, but very little known, is that a major hydrogen discovery was made. Am I going to try and pronounce the name? No, I'm going to cheat. In Mali in the 1980s. Folk were drilling for water, and they didn't find water, but they did find hydrogen. It's nowhere close to anywhere that you might expect to drill for petroleum. It's quite shallow. It has a bizarre cat rock, being dolerite sills, and there's maybe 500 billion standard cubic feet in place. However, when your security detail is the Wagner Group, it doesn't tend to get the press that it might otherwise do. And the cost of that, well, as you might imagine, it's pretty low. The cost of, it's not going anywhere, it is produced and used locally, but the cost of finding natural hydrogen should be much the same as the cost of finding the feedstock to manufacture grey or blue hydrogen, methane. Now, the generation of hydrogen, there are probably three mechanisms. I'm going to mention, well, I'll hint on the third one, which is something we're working on at the moment. The big one, which occurs geologically quickly in millions to tens of millions of years, is this serpentinization reaction. Peridotite plus water when it's hot, so 200, 300 degrees, you've got this coupled reaction between phosphorite and phaolite. The magnesium component hoovers up aqueous silica, something produced by the iron reaction. And in hoovering up aqueous silica, which sits on the right-hand side of the equation, it drives that iron equation further to the right, liberating hydrogen. The slow geological process, which runs for hundreds of millions and billions of years, is exactly the same one that produces helium, with the additional twist that not only does uranium and thorium produce helium, and in a moment I'll tell you how they do hydrogen, but when potassium also decays, although it doesn't produce alpha particles, it does lead to hydrogen production. And the reason for that is that if the alpha, beta, and gamma radiation as this decay occurs hit water, they will split it. Oxygen is in big demand in the subsurface, hydrogen not so, so the oxygen is mopped up by the rock, and we get liberation of hydrogen. There is an awful lot of water in the deep subsurface. You know, the deep crust is around about 1% porosity, and that is inevitably filled with water. And we see different products. So the first reaction, the water iron-rich reaction, produces near pure hydrogen, like the stuff in Mali, which is 97 point something percent hydrogen, and the lower reaction produces a mix of hydrogen and helium, and we've got the associated nitrogen. So in the Amadeus Basin in central Australia, you've got systems which are 10% hydrogen and helium, the balance is nitrogen. There's possibly a third that I'm trying to work out if it actually ultimately delivers hydrogen, and that's the high grade production of graphite, amphibole grade from organic matter. The last fling, if you like, of that process tends to produce the hydrogen. However, since it produces hydrogen following on from methane and undersaturated hydrocarbons, there's a chance quite a lot of that hydrogen will react with the undersaturated hydrocarbons and disappear anyway. So I've already jumped ahead somewhat because I've talked about the rates and the distribution of things like the Precambrian crust or the continental margins, and so we'll skip over that one a bit. Here shows you should look at the slides beforehand, because again the amount of water contained within the Precambrian fractured basement is not dissimilar to what we estimate is the total volume of fresh water on Earth. So lots of opportunities. And this gives some idea of the total volume. In fact, we've calculated, and this is quite a neat one, completely nonsensical in some respects, but the amount of hydrogen the Earth has produced in the last billion years could, if you captured every molecule, displace the current petroleum industry for 170,000 years. Now, clearly, most of that hydrogen will have ended up back at methane or water, or if it escapes as molecular hydrogen, rather like helium, it will zip off to the to outer space. But it does mean potentially there's a big prize to go for. Again, I've jumped ahead of myself. There we go. So again, we're trying to understand the geological processes, and they share much in common with what I've said for helium. Produced by slow or somewhat quicker processes in the crust, released from the site on production, transported through advection or buoyancy to the shallow crust, accumulating beneath aqueludes and trapped within the same sort of geological structures. The key thing about hydrogen, though, it's chemically very reactive, and particularly it's loved by microbes. There's a great piece of work by one of our co-authors, Rita, in South Africa. South Africa's got lots and lots of thousands upon thousands of wells for gold exploration, vent gases, and they vent a mixture of, or they did a mixture of hydrogen and helium. But over the last few decades, even though they've continued to vent, the quantity of hydrogen has reduced, and they're now venting CH4, methane. This is hydrogen from the crust, carbon added in by microbes, and they're acting, or they're processing that at the same sort of in a decadal rate. It provides us with some big concerns over geo-storage of hydrogen if ever we try to do that, because you could put hydrogen in the ground and get contaminated hydrogen plus methane back. Well, we've only really just begun the story on lithium. And if I take a quick look at that, salars, these high saline Andean type lakes where lithium is naturally concentrated in terms of parts per million, and you can see on the right hand side. But an awful lot of places contain relatively speaking, high concentrations of lithium, and they include some of the places that we know so well, like, for example, Weardale at about 100 ppm, or Cornwall at about 200 ppm. And certainly both in Cornwall and in Weardale, we're now looking to extract, in fact, Weardale lithium carbonate extracted already from those geothermal waters, and it's not using the same method. I'm not sure big salt plants in Eastgate would work particularly well, but it's using a different technology. It's using what's called direct lithium extraction, which is an ion exchange technology, and really puts back the water simply minus the lithium. So that, in fact, I've just said again there. And there are some demonstration early stage projects using this direct lithium extraction, whether it's in China, the USA, France, or indeed in the UK. Just very quickly, case history. I've already hinted at it. This is probably one of the most prospective basins in the whole of the globe for helium, the Amadeus or Amadeus Basin, as our Australian colleagues call it. And here you can see we've got a phenomenal mixture of gases. It's both a minor petroleum province and contains these helium and hydrogen, and possibly differences between the McGee well, which is essentially hydrogen-free, and Mount Kitty, which is hydrogen-bearing in terms of bacterial processes. So that's one of the areas in which we're working. The other thing to sort of think about is a really nice piece of work. You know, it's a weird story, this, but I ended up supervising a very good student from Bishop Auckland, who was at Southampton University for her dissertation, and she worked on helium in India. India really doesn't have any helium production, but it has massive helium demand. Nobody had thought to look at the hot springs. Nearly every hot spring that you can find in India, and there are many, is bringing helium out of the ground. The point being that we found helium by accident when looking for petroleum gases. When you look for it on purpose, it shows up. So, in many respects, these gases and indeed the solute of lithium haven't received much attention today. They are critical for the energy transition. You know, the helium exploration strategy we developed, and we tested it. Hydrogen exploration strategy in development. There are a number of hydrogen exploration companies around the globe now, including a new spin out from Oxford and Durham, which was launched last year with equity investment million. And lithium extraction and exploitation really has some go to increase the amount required by the developing through the energy transition. But there are probably lots of opportunities given the amount of pore fluid which comes out of the ground and no one's bothered to look at before. So can we meet demand? We will see. I think certainly for helium, we can meet demand. We can meet demand in a way that avoids co-producing greenhouse gases. A few years to answer that question, but it's such a topic at the moment that long. All that is indeed mentioned just before Christmas this year. Hydrogen, a term I made up. Australia, they nicked the idea. They drilled well to Adelaide, replicating a well drilled 100 years ago on Kangaroo Island, and they have found and produced hydrogen. We don't have many details yet, and we'll see what happens to lithium. But the signs are good. Fingers crossed. Thank you.
Thank you very much, John. That was fascinating.
And 39 minutes.
Does anybody have any questions? Either feel free to ask them out loud or pop them in the chat. Any questions for John? I can start. If everyone wants to think about their question. I was just going to ask John. I just wondered if I could just recheck. You were talking about what the CO2, the carbon dioxide footprint is of production of helium. Did you say that it was as big as the UK? Did I hear that right?
The global production, yes. So what I did was I took the current global production, which is divided between a little over 40% from the USA, where typically the helium is present as 0.3%, about 10% from Algeria, where the helium content is 0.19%, and 40% from Qatar, where the helium content is 0.04%. And I took the remaining 90-odd% or so and worked out what the carbon footprint of that was when it was combusted. And when you do that, the total for the globe is about the same as the UK's carbon footprint of around about 320 million tons a year.
Wow, that's wow. So yeah, amazing. I can see that Smith, you've got your hand up. Smith, do you want to go next?
Yes. Thank you very much, John, for that very interesting presentation. Though I'm not a geoscientist, I am more concerned about the energy transition discussion there. So, so in terms of what's the potential of this helium trying to, or what role do you think this helium will play in the energy transition? And
helium's in terms of the way we use helium, it's used for things like leak detection. It's used for certain types of welding. It's used as a safe lift gas. If you remember the contrast between the Hindenburg and the safe blimps we use now, clearly it's used for party balloons. But the two really massive growing bits of industry are medical cryogenics, the MRI scans and similar, and research cryogenics, and then manufacture of components for the energy transition. So the manufacture of computer chips or fiber optics. If you make fiber optics in a non-helium atmosphere, you'll get bubbles of gas in the fibers and they don't work. But because helium is so insoluble in anything, you construct your fiber optics in a helium atmosphere, and because it's so small, it gets out of any container. And I did do some a check on how many containers worth of helium is shipped to the Large Hadron Collider every month, and it's enormous. It gets out of jail every time. So those things do require. So it's an indirect. Part of the energy transition, but important nonetheless.
Thank you very much, John.
We've got a question from Will Nicholson. I can
if it's on.
I can read it if you like.
Lithium, Will, you can answer.
The question was, you go for it, Will.
Sorry, John. I was just wondering, what's inhibiting petroleum companies, which are already so rich in their oilfield assets, from actually looking at extraction of lithium from oilfield brines? Adding to that as well, would there ever be a sweet spot where these oilfield brines have a sufficient geothermal gradient such that you could, see them as both geothermal and oilfield brines and extract lithium from them, or is this not possible?
Part of your question, energy bill, but I think I know, not just with lithium, not just with helium, the whole use of materials is profligate. As a little boy, and I'm sure this was an apocryphal story, but I read a book about the Native Americans in the USA, what is now the USA, and they used every bit of the buffalo. They used the bones for making needles. They used the muscles for eating. They used the hide for clothing. They used the sinews for sewing, and so on. And that always struck with me. And what we don't do as a society, we've been throwing away stuff that we could use. So, for example, the reason I got into helium was that I spotted, when in the petroleum industry, that a field would be producing 300,000 cubic feet of helium a day. And even now, 30 years on, 25 years on from that discovery I made, and nothing has been done with that gas. Now, I think the reason for it is that although, if we take the oil industry, it's phenomenally inventive in terms of improving extraction of petroleum, better imaging of petroleum reservoirs, and so on. It's at the same time phenomenally conservative, because if you think about the North Sea, or think about the contrast between the UK land and the North Sea. On the UK land, we've purposely drilled half a dozen geothermal wells, and over the years, about 2,000 oil or gas wells, some of which have worked and some of which haven't. Offshore, in 50 years, we've drilled 10,000 wells. Some have found oil, some have found gas, some haven't. Every one of them is a geothermal well. Now, that's not to say we could repatriate the heat to shore, but there is actually a massive amount of heat which has gone to waste. By example of that, I'll come back to the onshore. The one geothermal well in the UK for an awful long time was at Southampton. It was producing hot water at 75 degrees centigrade from the Triassic Sherwood sandstone right beneath the city centre, and it was producing the water at a rate of 12 litres per second. If you go down the road a little way to the Witch Farm oil field, it's slightly cooler at 66.5 degrees centigrade. Its peak production of associated water from that field was 500,000 barrels of water a day. Now, until we did it, no one had thought to compare barrels per day and litres per second. But when you do it, you realise that the amount of wasted heat from the Witch Farm oil field, which could have heated every retirement home in Bournemouth, was 40 times greater than that in the Southampton borehole. And I think a lot of it just down, there are just different worlds. There's a water producing world, there's a petroleum producing world, there's a lithium mining world, and the protagonists never talk to one another. So we should.
Thank you.
We do.
Chris Groves. Chris Groves has a question as well.
Hello.
Hiya.
Interesting talk. Thanks, John. So I'm not an earth scientist, so some of it went over my head. But what I was interested in hearing your perspective of is whether we should be thinking of things like hydrogen and helium as critical resources. Because I work in PV, and there's a lot of thought about kind of like how much is available, how much is accessible, the dangers of artisanal mining and all that kind of thing. But should we be thinking of helium as a critical resource as well, and maybe stopping buying party balloons, that kind of thing?
Yeah, well, I knew you were going to say finish on that note. It is a critical resource. I think there's a lot more to be found. We know, for example, that a lot has been overlooked. During lockdown, myself and colleague Chris Ballantyne surveyed every country in the world to see if helium had turned up. And it tends to come in other guises, like the papers on hot springs in India, for example. So I think a lot has just been overlooked with the critical list, but every other year. And And the other thing which has happened to helium, which is important, is that for 100 years, through an accident, well, the whole industry was based on a falsehood, but the US dominated the market for 100 years. They were quite benign. Now we've got Algeria and Qatar. You remember a few years ago, Qatar was blockaded by Saudi Arabia. Had they not had some really problematic technical issues, Siberia would have gone on the act of producing helium in 2019. Fortunately, they didn't, because we've been hot. Actually, the story I heard, I'll come to you answer in a minute about party balloons. The story I heard this morning, the Siberian helium is now on production. The Russians are selling to the Chinese. The Chinese put together a bunch of helium. You can keep helium in copper-lined refrigeration copper-lined vessels. Put together a whole bunch of tanks and exporting them to Russia, and Russia filled them up. This is in the last year or so, and exporting them back to China. China's in big demand for helium, and when they got back, they were empty. Clearly, they need need a bit better seals on their system. But coming back to the party balloons, it's a bit like elephants. Seeing an elephant in a zoo is now quite difficult to do. But on the other hand, if there weren't elephants in zoos, most people wouldn't know about them. So in a sense, I think the party balloon is a very good way of meeting the public. I don't have a good answer, but I think there's something in that.
I'm sorry, you probably get that question quite a lot. I live in a world where there's lots of party balloons. But no, it's really interesting.
I must join your world. I must join your world, Chris, because I only see them now and again. Usually at a major anniversary I prefer not to have passed. So I
think Will had another question, and then if anybody else has any more, just pop in the chat. But Will, would you like to go next?
Yeah. Hi again, John. What do you think the security of lithium is going forward in its role in the energy transition? I recently read about graphene batteries. Do you think, to any extent, graphene batteries could replace lithium-ion batteries in their role?
Well, for something like that, I might come back to Chris Groves. Well, I will just touch on that. I should have thanked Will as well, because he was an undergraduate last year and now a postgraduate, and he's working on lithium, and he collected a lot of the data, which I then assembled into that graph I showed you, the blue and red bars. So thanks, Will, and great work. Funnily enough, there's a global shortage of graphite. You can make graphite. It's very expensive to do because you need amphibolite, 500 degrees centigrade. Most of the world's graphite is in Precambrian rocks, and it comes in different forms, some of which is more suitable for the batteries than others. But switching from lithium to graphite might make for a more efficient battery. I don't know. We'd have to ask Chris, but it actually makes the situation worse because graphite is in very short supply.
Yeah, and then there's also obviously the geopolitical thing with China and the US and graphite as well.
Yeah, and graphite, China's got a. I think that you're better one to answer this than I. But if we think about lithium, and if you broaden that graph that came from the data you collected showed about 20 or 25 different options for producing lower grade lithium resources from geothermal and other systems, but they're all over the world. So the problem, if we take something like the rare earth elements, over the past 3 decades or so, China has systematically bought its way into owning that, such that the Chinese have and freely talk about their complete domination of the rare earth market in the order of 97%. And they have used that for political purposes, stopping exporting critical rare earths to Japan a few years ago on the basis that a Japanese fishing vessel may have been spying in Chinese waters. The more you have a diverse array, and actually this comes into geothermal energy. Every country in the world's got geothermal. It might be slightly hotter than in Italy and Iceland than Iraq and Iran, to think of two more eyes. But it's present everywhere. And if you diversify supply, then you depoliticize games that countries play in terms of demand and supply and demand. And so diversifying the supply of lithium, which clearly is present potentially in many, many countries, would help.
Yeah, I agree with that. It'd be interesting to see if the West can sort of catch up with China in that sense.
Yeah, the Chinese have been very shrewd. I mean, of course, they will tell you, rightly so, they've been civilized for far longer than anyone else. But they've thought ahead, and of course, they can plan for a much longer time frame than is possible. So, very clever indeed.
Yeah, thanks, John.
Thank you very much, John. That was absolutely fascinating. If no one else has any questions, I don't think I could see any more at the moment. Then we'll say thank you so much, and thank you for joining this Durham Energy Institute seminar.